Today is just going to be a pretty simple introduction to your uh, contour integration and how you actually um, do some of the calculations and how that what you're actually essentially computing. We saw last time that we saw last time that you have so every time you go around a singularity you have 2 pi I collected around that singularity, right? So we'll try to understand how this works essentially, and we'll try to use this to compute some of the integrals. We'll try to see and arrive at methods where you use this idea to compute contour integrals with non-analytic regions in the uh, within them, right? So yeah, just give me a second. So 86. Okay. So so first we'll look at the what we did last time, right? So we saw how first we saw the Cauchy integral theorem. That is basically it says that if you have an analytic region here with like with some sort of a field or a function of the if you have an analytic region and then you want to compute the integral of a complex function in that within that within the contour, the closed contour. So you have it's essentially zero, and we saw how that works with Stokes theorem. Um, so we saw how to derive that with Stokes theorem, and then so essentially after that we saw one result, namely we tried to compute different integrals, and we saw that integrals of the form so integrals that have a singularity at z naught of at any point return the integral value to be 2 pi I. And we tried to informally understand what this actually means, because the idea is you can just take an integral around the singularity and then you end up looping around the singularity, so to remove the singularity, and that's how the singularity returns value. And also there's one more deeper like intuition, which is essentially that if you have a singularity, so when you map so when you take a Riemann circle or a Riemann sphere, so you can map your points at infinity to the pole of the sphere, which is the complex number I. So when you have the I axis and you map the infinity, you can map the infinities to the I axis. So you can just go through this how this works. So essentially, this is the Riemann mapping. So you can so as what happens here is so every time you kind of talk about a singularity, you do some because um, you can't express your infinity in terms of numbers. You go for the complex number. So you try to in some manner hide your infinity in the complex numbers. So this is one of the this is one intuitive idea, but so right now, coming back to like the okay, no. um, this this PDF is not opening for some reason, so just give me a second. uh, 57, yeah, right, got. Okay, so we yeah, so where we stopped off was this, right? So integral of f of z around a closed contour is 0, and then we took the example of a circle, and we took the example of a square, and then we saw that both the circle and the square essentially have the same integral, with a singularity, a circle and a square with a singularity, a circular contour. So again, note emphasis on the fact that the contour is different from the function. It's like the contour is the boundary and the function itself is the field. So it's two distinct things, not to be confused. The contour is independent of the boundary. Sorry, the contour is integral is independent of the field. So which is like saying that you have a field across space, and then it doesn't matter where, like how the field is shaped, as long as if you draw a contour in such a way that all your arrows are, everything, all the flux that is coming in goes out, you have the Stokes theorem applied. And that is what we saw essentially with the Cauchy theorem. So now let's look at how to use that to get something interesting, right? So for that, let's take a look at the Cauchy's integral formula, which essentially says um, which essentially says that integral, so 1 by 2 pi I integral over a closed contour of f of z with z minus z naught dz is equal to f of z naught. Yeah. So any idea of how this might come from? Where this comes from? An intuition? Okay, let's try shifting things around a little bit. So you have integral of c f of z minus z naught, where z naught is an arbitrary point. So if you have a contour, so z naught is an arbitrary point. Note that at z naught there is a singularity, because z minus z naught is equal to infinity, like 1 by z minus z naught is equal to infinity. So you have a singularity. So when you shift things around, you have 2 pi I f of z naught. So any further ideas? Okay. So technically the idea is that if you take the integral here, right? So if you take if you try to remove the singularity here, so what we do here is we say that we reduce this expression integral of f of g by g minus g naught dz is equal to integral of from 0 to 2 pi of f of c naught plus r e to the power of I theta by r e to the power of I theta So how are we writing this down? Note that the other key idea is basically you have you write down your point in your circular this thing. So you write down your z, the variable, in terms of your z naught plus r e to the power of I theta. So essentially you're shifting the whole contour to make that. So your z naught is essentially you're drawing a circle around z naught. Okay, so r e to the power of I theta is basically circle around the point z naught. So then what you set is then of course when you differentiate this, you have dz is equal to your dr is 0 essentially because you're setting r to be constant. So we'll always, so essentially what happens is whenever you want to talk about the complex circle, you want to keep r constant and you want to keep just one variable. So you want to shift all the burden of one complex variable which is the function of two real variables to just one real variable. So it is a trick that we are using, but the trick works. We'll see why the trick works, because so let's just write down this first. I r e to the power of I theta dz. So now the trick works because so now the trick works because when you want to take the circle, note that so first your z minus z naught is a pole, so we want to get that out. So we want to get a 2 pi I for a counter for the pole. So then so essentially what we do here is we know that in the region, so if we have the contour, the actual contour here, we know that the Stokes theorem applies here in the contour, right? So if we take some sort of a path such that so let's draw it a little more clearly. Okay, so you have this is your contour C, and then you have some singularity here at C naught. So then you can take, like we spoke last time, you can take a small circle around this, and then you can essentially put this. So you can take the contour, a closed contour. So note that everything here is closed, and you have only the area around the circle, which is a singular point. So you're eliminating that area in some sense. You're taking away that you are eliminating, or you're only tracking the integral of that particular pole around that particular pole. So what we do here is we express this circle as z naught plus r e to the power of I. So now obviously, so when you shift the origin, you have g naught plus e to the r, e to r theta. So yeah, so r e to the power I theta. So especially, so given this, so now we'll try to, so essentially what happens here is we have one more condition, that r vanishes, r tends to 0. So when you have r tends to 0, so you can evaluate this whole expression here as, because we know that Stokes theorem applies in all the other regions around that. So we can evaluate the whole thing by integral of c f of g minus g naught dg is equal to I f of g integral from 0 to 2 pi d theta. So this particular integral is called as a so this particular integral is the value of certain function. So note that what we have done. So normally what we would expect is, we would expect just a counter of 2 pi I, right? So why is that not happening? Note that you are taking this integrand is not f of z. Note that you have taken f of z separate out from the integrand. So your whole, like this is your, like the integrand, like the function that you are integrating. Okay? So if you take g of z is equal to f of z by g naught, g minus g naught, then your integral of gz such that there is no singularities will become 2 pi I. But because of the because you're taking a compound function, right? Because so you're essentially, you need to evaluate the function of that. So a function f of z. So essentially that is what comes here as your coefficient of the and this is f of z naught. Okay, sorry, let me just take f of z naught. So what the z naught is at that particular point. So now note that f of z naught, so if f of z naught is 0, so then you have the function to be 0 there. So f of z naught, so f of z naught is 0, then you have so when you evaluate this, okay, so given so when you evaluate this integrand by, suppose f of g naught is 0, okay, then this whole expression vanishes, like, so it's 0 by 0, and we can say that this is equal to 0. Okay, so it's just an approximation that we take, but yeah, so remember we made this assumption in the last video as well. So we just said that the moment you have 0 by 0, you don't have, like, you say that, like, it's all 0. So like it's saying that once you draw a small circle around that, there is no flux coming into the singularity nor any flux going out of the singularity. Therefore you don't have any, like, so you can cancel out the zeros with respect to each other when you have a 0 by 0 integrand. But the moment you have a singularity, obviously you need to evaluate it, so you just have f of z in the integrand. So you can actually calculate the integral and see it for yourself, but this is the essential intuition behind that. And now let's use it, like, so yeah, so now we have in the limits of r is equal to 0, we essentially obtain this is equal to 2 pi I f of z naught, which is the value of the integrand, which is of the integral. So we have so again what we can ask is z naught within the contour or within, is it outside the contour? Because it doesn't have to be necessary that z naught is within the contour, right? So z naught can just be any random pole of the function, and you can just have it outside the contour because obviously, so if your z naught is here, and then you have a singularity of you have a singularity at point z naught, right? Now you can define, because your boundary itself is completely independent of the points that you're selecting, the internal regions, the function, the field that you're evaluating. So you can have some sort of an arbitrary boundary here, right? So in that case, guess what your integrand would be? Yeah, any guesses? Just think of it, just think of it. Does a singularity which is not within the contour affect the integrand or the integral? Are we, in other words, to obtain Stokes' theorem, like to get the integral of 0, are we trying to remove any point? So then what do we have here? We essentially have the Stokes theorem, right? So this is 0. So you don't even have to consider it. So it's just a way of writing that particular function, which doesn't really matter. So our singularities don't bother us because it's not affecting our integral. Just in the very same so every function. So for example, in the real case, okay. So if you have x and if you have f of x. So suppose there is a singularity at x naught. Okay, the whole f of x is integrable for all regions outside f of x naught. The single point f of x naught or x naught. So essentially it doesn't matter what this thing is. So this is let's see, this is infinite. Okay, so if you have some random function and all this is completely integrable, the only thing is you cannot, so as long as, so when you define your boundary, okay, so you have x1 to x2, so if your integral is not between x1 to x2, okay, or I'm sorry, if your singularity is not between x1 and x2, then you don't get your x, so x naught plays no role. So that is exactly the same, you're just writing the function down this way, but it actually just plays the complex number just really, the denominator being 0 really plays no role. So that singularity doesn't matter because you're calculating your flux or whatever it is just completely outside. you're calculating your line integral outside like the vortex. So it's like saying, so if you have a charge at a point and then you have like the Gauss law outside that point, right? So the total flux there, like at a volume like away from the point, is zero. So you don't have a flux there. So it's essentially the same thing. Right? There is a charge, okay, there is the charge that is giving the shape to the whole thing and all of that. But it doesn't really play a role when you do compute the Gauss law. So now let's just like do a simple example. Let's say we want to find out the integral of some contour of dz by z into z plus 2. Okay, then we have essentially this is going to be 2 pi I evaluated by this whole thing f of z naught. So the singularity is that minus 2, right? Sorry. Yeah. Wait, 1 second. So yeah, so f of z is equal to, so your f of z is equal to 1 by z plus 2 and z naught is equal to 0. So you have this, there's basically 1 by z plus 2 at z is equal to 0, which is equal to pi I. So you're evaluating z is equal to 0 and then you have to pi I. So the 2 gets cancelled out and you have pi I. So you can just go through this example like how so yeah, so essentially, so because z okay, right, so what did I forget to mention here? What is not making sense? What's not making sense? I haven't specified a contour. So I haven't specified a contour, and right now I'm just saying there is an arbitrary contour, and then I want you to compute this integral over the contour, right? Without even like talking about where the contour is, right? So in this particular example, so we want z plus 2 to be like, it should not be a singular point, that is it should be a singular point outside the contour, and essentially to simplify the whole thing, the contour, like for the sake of this problem, like for the sake of this example, we have the contour actually to be the unit circle. So now the point z plus 2 is outside. So then you can take this as you can take f of z as 1 by z plus 2, because that is what your contour. So your z is your z naught, okay, and like your essentially the singularity is at z naught. So you have z plus 2, and yeah, you're just evaluating from now. The whole thing makes sense, because earlier it didn't really make sense. So you're taking this and then you're essentially applying the same thing, the same results that we have here, whereas yeah, so you're applying this 2 pi I f of z naught. So your z naught is 0 and your f of z is 1 by z plus 2. So then you have the integral here, you have the integral here, and then 2 pi I f of z naught. So this is your f, and then you're evaluating at z naught. So you have 1 by 2 pi I. So you have pi I. that is the count, like, so essentially, so can you like guess another probably intuitive idea that comes in? I don't know how this is true, but essentially what I'm thinking of is, okay, so I don't know how true this is. Again, disclaimer, misdirection alert. So, right. So essentially you have this, right? You have some sort of a contour, okay? You have a contour, and then you have a singularity here within the contour, and then you have a singularity somewhere outside within the contour. Now we are evaluating the integral of the singularity within, like integral within the contour. Now, does that mean the factor that you're adding, does that come from the fact that there is a singularity outside the contour as well? Because it seemed to me in this example that you have like two singularities, and then you're cutting. I don't know how exactly this is related, but essentially, I mean, of course, it is because of the fact that g plus 2 is the denominator. So, for example, if you have g plus 3, then you would have 1 pi 2 pi 2 by 3 pi I, right? But the idea is that your coefficient entirely arrives just because of probably arrives because of the singularities that are present outside the contour that you are taking. So this is just an idea again. There might not be an exact correlation. Probably try like I'll probably try to read up and come back to it later. But essentially, once we have done this example, we just go through another thing, another simple like trivial example. So, I mean, an intuitive sketch rather than an example. So now we have a contour, and now we have two singularities here. Okay. So note that you can take last time we spoke about how the integral can be the contour integral now can be taken like this, right? So you can take this, and then you can have this surgery, and then you can come here, and then you can have this surgery as well. So you can have some sort of an integral like this, the contour like this, where we're essentially taking away this point, right? So similarly for multiply connected regions, so we arrive at the definition of connection, like connected regions now. So what the connected regions essentially mean that given that you have um, analytic, or sorry, you have a contour in which certain region is not analytic, okay, but you are not integrating over that region, right? So what then you do is you just, how do you evaluate this particular integral? So because you're trying to say that given a contour, I don't have an analytic region, and I don't want to take the integral of that analytic region. So how do we do this? So what we do now is we break our problem down, right? So we just say that, okay, there is one particular integral that I'm taking, and there is two integrals that I'm taking. Okay, now I'm evaluating the integral between these 2 points. So note that this is not in the contour. Note that the non-analytic region is not in the contour. Okay, so now can you guess what it might be? What the integral of this particular, so given that this is C1 and C2, any guesses? Let's come on, you got this. Okay, that's good. That's good. So 1 of f of z dz plus integral of c2 f of z dz. Right? Yeah. Now take the guess. It's smooth, continuous, analytic, and it is differentiable. Like it has no singularity. Both C1 and C2 have zero singularity. So what is this going to be? So Stokes theorem, Cauchy's theorem. Yeah, exactly. Because this is 0 and this is also 0. So what you do is you're essentially just talking about some weird way of writing down your contours. There is no singular regions here. So you just have 0 there. And then again, of course, if this has some sort of a singularity, you obviously need to take that in account. So if there is a singularity here, you just need to take that into account. But if there is no singularity, then it's all 0. So this is the idea of like connected region. So if you have like one connected region, and then you just want to evaluate your integral in the analytic part of the connected region, it is still perfectly fine. It doesn't lead to any anything majorly new. Now note that, okay, so this was a slight detour. Coming back to our Cauchy's integral formula. So what we have here is integral of c 1 by 2 pi I f of z by z minus z naught dz is equal to right. So we have this. Now what we do here is we try differentiating f of z naught. Okay, so we arrive at 1 by 2 pi I integral of f of z by z minus z naught the whole square. So now note that the entire idea of your variable shift from your integrable variable shifts from the is different from the differentiated variable. How does this play out intuitively is something that you need to think about. But essentially the idea is that you differentiate a function, you differentiate where you play around with where your singularity is. So you have different curves based on where your singularity is. You can have lines of singularity, you can have some sort of f of z naught. So your g naught no longer is a point, but it's rather some sort of a function or some sort of a curve. So now we want to evaluate the singularity around or above this you want to evaluate the differentiation of this particular curve, right? So then you have this dz. That is why obviously you have no coefficients coming out, right? Or else like you don't have any factors of f of z itself. Or else obviously if z was a variable you would have factors because z is independent of z naught. So again, subtle points, but it's very quite crucial to remember. Now that you can also take this. How do you exactly take this? Well, pretty abstract, but you can take this particular differentiation, right? And then f double differentiate this, you get 2 by 2 pi I of f of z dz by z by z naught whole square. And then you have like so on, and fn, so the nth derivative of z naught is equal to n factorial by 2 pi I integral of f of z dz by z minus z naught to the power of n plus 1. So this is called the derivative formula. Obviously you do have applications for direct derivatives in terms of different when you have like differentiation of a different variable, like two complex variables, and then you have the differentiation of one under the integral sign. You can play around with it. It does have a like own mathematical theorem application, but essentially what it says is that your function is it proves an interesting, it proves helps us look at a couple of things. One is if so it is analytic, so it guarantees, so your analytic requirement, okay, make sure that you're not analytic in just the first derivative, but in all your derivatives. So if your point is outside the contour, so then you have any derivative of this particular function and it's still like it's analytic, and therefore it can also be integrated, it can be further differentiated. So like right, and it essentially talking about differentiability here. You can't so your upper limit is f of z, your upper limit of is f of z, but beyond that, once you differentiate with respect to z naught, you keep differentiating, you have conditions for analyticity. Note that this is like two different variables, two different complex variables that you're playing around with here. So the whole imaginative process is like a lot more, you need to imagine a lot more in order to like get the true like meaning of this whole thing. But this is the essential idea, right? So there is some sort of an upper bound, but like for analytic region, like you have any number of derivatives that are analytic, right? So you have your singularities only at z naught. It will seem like, okay, if you look at that, it seems like you have you have like n g naught, but note that like there are again specific conditions. So where your z naught is equal to z. So that is only like yeah. So again you have two functions of g and z naught, and then you just look at this, right? But also another thing that we can think about is like, okay, even if your z naught is arbitrary, right? Suppose there is a singular z naught, right? A single constant z naught, but yeah, you have f of z naught, right? So based on how you select your f, or based on how z naught is located, so no matter what given within that integrable region, you have only one singularity, right? So no matter how many powers there are, you have one singularity. So you have one per pole per se, even if you differentiate it to the n orders. So these are like different interpretations that I can give to the whole thing. But essentially note that this result is pretty like it's pretty useful to just think about. But also yeah, so you can just you can use it like you can go through to the text for like more on the applications and all that. But from now let's look at one last idea, intuitive idea. So given the so what did we so now we have f of z is equal to 1 by 2 pi I integral of f of z prime by z prime minus dz. So note that we have completely switched the like the notion of what is a function and what is a fixed point here. So again, this is something similar, right? So now we are assuming that we're like let's see what we're trying to do here. Okay, so this is equal to 1 by 2 pi I integral of f of z prime dz prime by z prime minus z naught minus z minus z naught. Sorry, wait, I made a mistake here. Yeah, so there's no dz in the denominator. That doesn't make sense. Huh? So right, so now we are essentially talking about one point g naught where we have noted singularities in terms of both functions of z and z prime. So now looking at this, so we can actually represent this integral. So okay, so we can represent this integral, we can further write it down in terms of 1 by 2 pi I f of z prime dz prime by z prime minus z naught into 1 minus z minus z naught by z prime minus z naught. So we have further simplified the whole thing down. So we have just taken this out and then we have just written it down. Okay, we have taken z prime minus z naught outside the bracket and then we have written it down. So the denominators cancel once you put it in the bracket. So that's the simplification that we have done. So the idea now here is that you can, so we notice one more thing. We just notice that 1 by 1 minus t can be written as 1 plus t square plus t cube, so on. This is basically this is the Taylor expansion, right? This is I mean this is the identity. So this is the identity, right? So this is basically the summation of t to the power of n. N is equal to 0 to infinity. It's the so now what we do here is we say, here's the tricky part, right? F of z is equal to 1 by 2 pi I integral over the summation of n is equal to 0 to infinity. Then we have z minus z naught to the power of n f of z prime dz. So essentially we are just expanding this whole term. We are expanding this whole term using this identity that we have here, and we are writing it down by g prime minus g naught to the power of n plus 1. Why is this one not being written? Okay, yeah. So now, okay, so now we just put the summation outside and we take the integration inside, because here z minus z naught is independent of z prime. Okay, sorry. So your g minus z naught is independent of z prime, so you can take the whole summation outside. Okay, so what you can do is you can then represent this as 1 by 2 pi I summation from n is equal to 0 to infinity of g minus z naught to the power of n integral of f of g prime dg by z prime minus z naught to the power of n plus 1. Okay, so now this is basically, we have seen this somewhere. We have seen this formula somewhere. Yeah, exactly. So you have f of z is equal to summation of n is equal to 0 to infinity the n derivative of g naught by n factorial g minus g naught to the power of n. So this is your expression for your Lorentz, this is the complex Taylor expansion. So now, so again, you have all the ideas of your Taylor expansion here, right? So you have you can probably take this to the idea of like a delta, and then you can just evaluate other expressions as well. But essentially, so this is, so the idea behind this actually is really interesting. So in order to talk about this, it's as fascinating as it is difficult to talk about. So right, so let's just try to figure it out anyways. Okay, so you have a region, right? You have a contour, and within the contour, what you want to do is to essentially have, take some point G, take some particular point z naught. Now what you can do is you can expand z in terms of z naught by taking a contour integral around z naught. Okay, so this is an arbitrary closed contour. Okay, and how does this exactly work is because you have your so how does z prime play into this whole picture is basically you have this to be defined by z prime, f of z prime. So your contour, so you can take some arbitrary section of the contour, like you can take some arbitrary section of the contour, like kind of contour that encapsulates Z, and then you can expand Z around this contour, because then note the Stokes theorem still applies. So you have some sort of like, because of your, so it's a pretty like back and forth kind of thing, because you, when you're talking about your Stokes theorem, you're talking about the integrand being 0, and then you're also at the same time you're defining your Z naught to be a pole somewhere, and you're expanding around that particular pole, but also you're expanding Z, which is like a point, but you have converted that to a status of a variable. So right, so all of these like mixes and matches are happening, right? So now your idea of what it is to, so your Z prime now just becomes a idea of it just becomes about the contour now. So it doesn't become it's not anything else, but it just becomes a contour. So note that the external yellow contour that we have here is not essentially very important, as long as it is an analytic region. So your contour is actually given by Z prime. So now you you reduce the role of Z prime to the role of just being a defining the contour, right? To take this, to be able to take this particular expansion. So that's how you write it. That's how you write, like, so essentially you write Z as a contour, and then obviously you make this whole thing smaller and smaller. Like you reduce, as you take an higher powers of n, you make this whole thing smaller and smaller, and then you are essentially circling around Z itself. So how does that work? So instead of taking some sort of a contour like this slowly reduces to Z naught, okay, and then you have Z, and then you have just this, and then everything else is excluded. This becomes your f of Z prime at different point or values of different time. So that happens as n tends to infinity. So you have f of Z. So I mean, this is a really subtle and abstract idea. Okay, also note that Z is not necessarily like it can be a pole, it need not be a pole. So it's like I mean, yeah, so if it is a pole, then you have like a different sort of an expansion, right? If it's not a pole, then you have a different sort of an expansion. So I mean, like, essentially the same idea works, but it doesn't matter if Z is a pole or not. So yeah, so this is the idea for your Taylor expansion. So basically from here we can actually like say that so you can divide, so the idea becomes divide your circle, like you divide your contour region into different parts, and now you have this the Laurent expansion, which is essentially, so you have so you have your f of, sorry, let me just do this, right? F of Z is equal to integral 1 by 2 pi I of contour 1, where f of Z prime dZ prime by Z prime minus Z minus 1 by 2 pi I integral of C2 into f of Z prime dZ prime by Z prime minus G plus and then so on. So you can have like, so additional terms. So you can essentially expand this whole thing, the integral in terms of a series. I mean, and then so you essentially what you're trying to do is you're trying to get everything in terms of like singularities, and you want to calculate. So you want to give you want to give certain values to the points at each singularity. So we'll go a little more into detail in about into the Lorentz expansion, and we can actually like from there we'll look at how singularities and zeros are connected, and we'll look at a couple of other interesting terms later on, but this should essentially cover like what I was trying to talk about. So right, so how do you what you need to remember so far is like you can have, okay, so let's just do a quick refresher. Right, yeah, so we have the Cauchy integral formula where where you have your evaluation of 2 pi I f of z and f of z naught, which gives you the integral around a particular in the form of, if the integral is in the form of f of z by z minus z naught integrand, sorry, and how we saw how that works, right? We saw the idea that you're taking and you're making a narrow circle around that, and then you're taking the radius to tend to 0, and then we saw that like outside the contour, like if there is a singularity, it doesn't really matter because it's definitely not part of the boundary condition, like not within the integrated region. So you just have the Stokes theorem there. So the Cauchy theorem there. So the integration will be 0, and then so we saw this particular we saw a particular example, and then from there we looked at how the derivatives, or how you differentiate when you take the point, right, the singular point, and then when you make that a function itself, then how do you take differentiation with respect to that, and then you arrive at a series, and basically using the help of the series we evaluate an expansion around a particular point and a singularity. So this is, we look at the Taylor expansion. This is essentially the Taylor expansion, and then it works. Note that the Taylor expansion works only in analytic region. So you can't again have this whole thing, or if you're if there is any other point than Z which is singular. Right. So we just saw this idea of expanding your complex Taylor expansion, and then we hinted on the idea. Okay, so what do you want to do with Lorentz series in a simple, in a condensed manner? Just some food for thought is that you want to write down every integral as some sort so if you have some sort of integral of f of z dz, you want to write it down as integral of f of z prime dz prime by z prime minus some arbitrary z naught plus some other integral of, okay, so this is not a, so it can be g, right, it can be g or whatever, so plus g2 of z some other 2 dz2 by z2 minus z naught plus so on. So basically you just have or you just have like and collections of singular points. So it's like probably you want to evaluate g1, g2, and so on. So essentially what you want to do is you want to collect each of the singular points, and you want to be able to define the singular, like you want to separate out each of the singular points. So that can be done using the help of Taylor expansion and the yeah, everything that we discussed so far. So given that all of this is the idea, essentially, tomorrow we'll look at how exactly this works. So what exactly we're doing. So this is just an intuitive sketch out there. Most of the it's pretty wrong. Like nothing is right in the particular expression that I've written, but that is just the intuitive sketch of the whole thing, and we'll see how that works tomorrow. Alright, so let's stop the recording now. Before that, any question?